All right, welcome back to day 2 of Logs and Exponentials. At the top of the page, you'll see 3 formulas that are not given to you on your reference sheet, so you definitely need to memorize these 3. The first one is just your basic exponential growth and decay. The second one is if it ever says the word compounds, that's when you need to think in terms of compounded monthly, quarterly, daily, weekly, and that's what's going to change the n value. And then PERT is when it says compounded continuously. So let's look at our 3 examples here. Michelle invests $3,500 into a savings account compounded quarterly. That's going to be your middle formula. The interest rate is 2%, so R is going to be 0.02, 5 years, that's your T value. Compounded quarterly, that's your N value. Quarterly would be 4 times a year. And if she invests $3,500, I would plug that all in for P. 1 plus the rate divided by the number of compounds raised to the 4 times 5. And you would literally just type that in your calculator and round to the nearest penny, which ends up being $3,867.13. The middle one, letter B, says a car is currently worth $9,250. It's been depreciating, so that's a key that it's going to be decreasing, so you're going to use the 1 minus formula. Over the last 10 years at a rate of 12%. So again, if the rate is 12%, that's 0.12. The car is currently worth, that's A. It wants to know how much did they pay for the car when it first was purchased. So that's your principal or initial amount. I don't know P. And it says over the last 10 years, so time is 10. So I'd have 9,250 is equal to P1 minus the rate because it's depreciating over 10 years. Type this in your calculator, divide it to the other side, and you can solve for how much the car was worth initially, again, to the nearest penny or cent. Third one, Nancy invests $300 into a savings account compounded continuously. That's PERT right there. All right, so we have an initial amount of $300. E is going to be the base this time. The rate goes into the exponent, so 0.013. And in a decade, remember that's every 10 years, so 10 years later, how much money will she have? And that's going to be $341.65. All right, moving on to our favorite topic probably of the whole year, and that's very thick sarcasm there, is mindful manipulations. You're going to find a lot of these on your classwork tomorrow. We just do 2 examples here in our review. So the first one says the population of deer in Erie County is growing at a steady rate of 7.3% per year. If this trend continues, write an expression that could approximate the monthly increase of deer. Let M represent months. So we know our yearly growth rate, and if it's growing, it's got to be greater than 1, so it's going to be 1 plus 0.073. Now, if they're telling us to use the variable M, and they're giving us a yearly rate, then I need an exponent that represents a year. So this exponent, m over 12, really means once every 12 months. Well, once every 12 months is AKA a year. Okay, so that would be a yearly equation. But if it wants me to convert a yearly rate to a monthly rate, think about it. If it's growing 7.3% per year, then if I want to look at a fraction of that, a 1/12 of that, it's going to be a smaller rate that it's growing per year. So what you want to do is you want to bring that 1/12 inside and leave the M on the outside. Now what this is representing is once per month. And so whatever this is in my calculator, that will represent my monthly growth rate. So if I bring up my calculator, it is going to be 1.073. Now this is where I saw a lot of kids throughout the year make mistakes. It has to be raised to the 1/12, not times a 12th. All right, so the base ends up being 1.0059 m, and it says find the monthly percent increase. So if I convert that back to a percent, it's about 0.6% growth per month. Letter B, it kind of goes the other way. So that's converting to yearly. The next one is taking a yearly growth rate because it says T is in terms of years here. So that means it's growing 25% per year. I want to know then how much is it growing per month. So this is where you actually balance the equation. And if you want to balance it, since I want to create a smaller increment of time, weekly is smaller than yearly, I'm going to bring in, a 1/52nd, because there's 52 weeks in a year. And to balance that, I put a 52 on the outside. This means 52 times per year, which is weekly. This is going to give me my weekly growth rate. So again, I type that in my calculator, I get 1.0043 ... And so if it's asking for the weekly rate, the rate it's growing each week is this. And if it ever asked for the percent it's growing each week, it would be 0.43% growth per week. Okay, the next little part here is solving fractional equations rounding to the nearest hundredth. However, I will say the first two examples, A and B, we have already done that because those actually aren't exponential equations. Those are power equations. Notice the variable is the base. We've already covered that in a different unit, so I'm going to move on to letter C and D. What we want to do is we want to get common denominators, so we want to get common bases so we can drop the base and just solve for the exponents. So what we need to do is rewrite 8 and 1/2 as a similar base. So I can rewrite 8 as 2 cubed, which works very nicely. And I can write 1/2 as 2 to the negative first power. Because remember, negative exponents reciprocate and that makes fractions. Now that they both have a base 2, I can drop the bases and all I have to do is solve for the numerators. So 3x squared minus 6x is equal to -1. Get it equal to 0. And because this has a coefficient and the triangle method isn't going to work, I would have to jump to the quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And when I type that in and get the discriminant, which is 24, the directions here say round to the nearest hundredth. So I would literally just type this in my calculator and get my two values and round. So it ends up being 1.82 and 0.18. All right, letter D, very similar, but it looks different because it has this multiplication sign here. So again, I still want to get all in terms of bases of 3 in this case. So 3 to the what power is 9? Hopefully everybody agrees that's 3 squared. 3 to the third power is 27. And 3 to the fourth power is 81. I now have common bases. However, and I'm going to do this off to the side a little bit, if I ask you to do, let's say, x to the third power times x to the fifth power, I hope you all say x to the eighth power. And what you just did with these two exponents is you added them. That's exactly what I'm going to do with these exponents. I'm not going to multiply them because when you multiply, you actually add your exponents. So when I go and drop the bases here, drop, 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 it's going to be 2x plus 3x minus 9 is equal to 4. Combine like terms, so I get 5x minus 9 is equal to 4, 5x is equal to 13, and therefore x is 13/5. Whoops, sorry. All right, expanding, condensing, these are your rules here, already filled in for you, and I'm not going to take the time to do every example. I'm just going to do B, C, and D here. So in letter B, if it wants me to expand or condense, in this case, we are definitely going to expand. This is already condensed. It's written as a single log, and that's a huge indication. If it's written as a single log, then the only way you can go is to expand it. So maybe my first rewrite, I would notice that there's a square root around it. So natural log of x to the 5th, y to the 2nd, all of that to the 1/2. Because remember, power over root is the same thing as a radical. Well, exponents, according to our rules in those boxes there, that needs to be pulled out front. So if I pull that out front, I have 1/2 parentheses, because everything was being square rooted, so that means I need parentheses around everything. Natural log of x to the 5th. And because these are being multiplied in here, we know we can separate those with a plus sign, so natural log of y squared. And then again, I have exponents that have to become coefficients. Same thing with this 2, has to pop out front. So 1/2 parentheses 5 natural log of x plus 2 natural log of y. And that would be as expanded as you can. If you really wanted to distribute that 1/2 out, you could. You do not have to though. All right, so let's expand letter C. Again, I knew it needed to be expanded because it's written in terms of a single log. I'm going to write it in terms of multiple logs. All right, so the first thing I want to do is maybe get rid of that division. So maybe natural log of xy cubed minus natural log of z. So now I got rid of the division. Now let's get rid of that exponent here. So I have 3 parentheses natural log of x times y minus natural log of z, and I had to close that parenthesis off because that 3 is only an exponent on the x and the y, so it should not be distributed to the z. And then last but not least, multiplication, I can expand those logs by using a plus sign. So natural log of x plus natural log of y minus natural log of z. But lastly, for this section here, clearly letter D is expanded. There are 3 sets of logs. I need to condense them down to a single log. So let me deal with these coefficients first. The 1/2 is going to become an exponent. This 2 is going to become an exponent. So I have 3 log base 3 of a to the 1/2 minus log base 3 of b squared plus log base 3 of c. Now, I might skip some steps here, but we know that this plus sign is really multiplication. We know that this subtraction is really division, and we just talked about this on a previous example that the exponent of a 1/2 is really the square root of. So this would be log base 3. We have the square root of a on top, and it's divided by b squared c. So it's written as a single log. No, shouldn't have the word log in there multiple times. All right, so using our expanding and condensing, I'm jumping down to letter H now. It says using your log properties determine the transformation. So I notice again that this is in terms of a single log, so I want to expand it to the best of my abilities. So if I expand this, I have log base 2 of 4 plus 3 log base 2 of x. And if I type log base 2 of 4 in my calculator here, so if I gotta turn this back on, log base 2 of 4, if you don't already have it like kind of memorized in your brain here, it's really just regular 2. So this is really 2 plus 3 log base 2 of x. And now that I have this completely expanded, this 2 tells me to shift it up 2. And this 3 is actually a vertical stretch. The important one for logs, because they are inverses of exponentials, remember they have vertical asymptotes. So what we need to worry about is our horizontal shifts, not so much our vertical shifts up or down, but the left or right. So if you expand a log and you have something in the inside adding or subtracting to x, that's going to be the important one because that's going to tell you where the asymptote goes. So that's left or right, and it tells you where the asymptote goes. So if it shifts it left, it will be at negative something. If it shifts it right, it will be at positive something. All right, so now we get into actually solving either exponential equations using logs or solving log equations using exponentials. So it can kind of go either way depending on what the equation looks like. So number one, we have basically a sequence. It's asking for the explicit formula for the following sequence. What I notice is to get from 5 to 20 and 20 to 80, I have to multiply by 4. So that tells me it's a geometric sequence. So if the value of the first term is 5, my common ratio is 4, and it's raised to the n minus 1, and it's asking what term in the sequence is 327,680. And it's asking me to use logs to solve this. I think the first thing I would do is divide by 5 to isolate the exponential to the best of my ability. I get 65,536. And I could here technically get common bases and drop the base, but if we want to actually utilize our knowledge of logs, I would do log base answer power. And so when I type that in my calculator, log base 4 of that long number, so let me do that math, log base 4 of 65536. It actually turns out to be a really nice number, so therefore it must be the 9th term in the sequence. Similarly, what if I read compounded continuously and it wants me to solve? So Henry wants to deposit $150 into a savings account with 3.1% compounded continuously. That's PERT. We just talked about that formula on the last page. He wants it to grow from 150 to 600. So he wants it to be 600. He starts with 150. The rate is 0.031. How long will it take? So again, isolate the exponential to the best of your ability. So divide by that coefficient. I get 4. Now we have to think about what is the inverse, or how do I undo an e, an exponential with a base e? Well, that would be a natural log, because natural logs have a base e, so BAP, base, answer, power, and then divide by the coefficient there, and round. It doesn't have rounding directions, so we'll say about 44.7 years or so. All right, these are just straight up solving examples here. As I was saying before, you always want to isolate the exponential first, and then since it is an exponential, to undo an exponential, you're going to BAP it. So log base answer power, and then again move that 3 over to the other side, get x by itself, and if you need to round, feel free to round if it says to. Add the 2, again, isolate the exponential. The log that has a base e is a natural log, base e. You really don't need the e there because natural log, that's the assumed base, of 14 equals the power. Move the 2 over and type it in your calculator. And again, if the directions say to round, just be sure to round. Moving on to number 6 here. This is starting as a log, so not an exponential, but it starts as a log. And for me to be able to do anything, I need to condense my logs together. So we just practice that at the top of the page. So if I condense these logs together, I know that a plus sign really means to multiply. So if I multiply those two together to undo a log, remember LL, I can lasso a log. So the invisible base is a 10, so 10 to the first power is 10. I'm going to FOIL that out. So x squared plus 7x plus 10 is equal to 10. If I get it equal to 0, the 10s cancel out. So I have x squared plus 7x is equal to 0. GCF. Oh boy, where did I go? Sorry about that. Equals 0 over here. I'm running out of room. One of my answers is 0. One of my answers is -7. And then please check your solutions. You actually cannot take the log of a negative number, and I'll show you. If I type in log of -7, negative 7 plus 2. So hopefully you agree that negative 7 plus 2 is still a negative result. My calculator will tell me non-real answer. So this one actually rejects. So my only solution is 0 on that one. The only other way that you could solve logs is something like number 7. So we have this 3. So the first thing I would do is log base 7 of x cubed plus log base 7 of 2 is equal to log base 7 of 16. Luckily, they're all log base 7s. If they weren't, I wouldn't be able to do this. Again, this plus sign tells me I can put them together. So log base 7 of 2x cubed is equal to log base 7 of 16. This is where I called drop the logs because you have the same log on both sides. It's kind of like dropping the base. So then you just solve for what they were taking the log of. Divide both sides by 2. I get 8, and the cube root of 8 is 2. All right, bear with me here. 2 more examples. I'm going to do 9 and 11, and then we'll call it a day. The Richter scale measures the magnitude R of an earthquake, and it's defined by the following formula. In 2011, a quake measured 6.3 on the Richter scale. In scientific notation, rounded to 3 decimal places, how much energy was released? So 6.3 on the Richter scale means I'm replacing R with 6.3. And just like we were doing for the exponentials, you need to isolate the log to the best of your ability. So the first thing I would do is move the 1.46 to the other side. After that, we're going to divide by 0.67. So here I get 4.84. And divide by that 0.67, the coefficient there. And when I divide, I end up getting this 7.2238 ... I finally have the log as isolated as possible, and just like we've been doing, you lasso a log, so the invisible base of a log is 10. All right, so I'm going to have, and let me bring up my calculator here. All right, so we have 4.84 divided by 0.67. There's that 7.22 number. So I have 10 raised to that answer. All right, so lassoed that big number there, 167, whatever it is. I wish that would stay up as I'm typing, 44824. Divide that by 30.37. Take that answer, divide it by 0.37. Okay, let's think about this because the directions say write it in scientific notation, rounded to 3 decimal places. So rounded to 3 decimal places would be 4.526. So 4.526 times 10, and then we have to figure out what our exponent's going to be here. So times 10 to the, that was 1, 2, 3, 4, 5, 6, 7 swings. So it'd be 10 to the 7th power. All right, last one, half-life here. You're observing a mystery isotope. At 12, there are 3 grams, and at 6, there are 1.1 grams. What is the half-life? So let's think about that. If we consider 12 p.m. to be our initial time and our initial amount, then we are starting with 3 grams of some substance. And by the time it gets to 6 p.m., which again is 6 hours later, okay, so it's 12 p.m. to 6 p.m. is 6 hours later, that's T. There's 1.1 grams of the substance left, so that's our final amount. So, as I've been saying this whole time, isolate to the best of your ability. Solve for H. What we're going to do here is map this, so we're going to have log, base, answer, power. Type that in your calculator, cross multiply to solve for H, and round to the nearest hundredth it asks, so it's going to be about 4.15 hours. All right, see you soon. See you soon.